Okay, so in this screencast, we have a request from an Orion problem to propose a molecular formula given the following data. The parent ion M is at 167 and has 50% abundance. The parent plus 1 ion is at a M over Z of 168 with 4.4% abundance. So given these pieces of information, how can we propose a molecular formula? So let's write down a couple of clues here. So number one, the parent ion has an odd mass. That's important because that indicates there is an odd number of nitrogen atoms present. So for the sake of this problem, let's just assume that n equals 1, so that there's one nitrogen atom. So if we do that, we can take 167 minus 14, that's the atomic mass of nitrogen, and that gets us 153 mass units remaining. And so that will contain carbon, hydrogen, and any other elements. So our second clue here, we can rule out that chlorine and bromine are not present because in the data that we're not given any M+2. So since there's none of that, we can rule out So we're going to rule out chlorine and bromine since there is no significant M+2 ion listed. So, and again, chlorine would have a 3-to-1 ratio of M to M+2. Bromine would have a 1-to-1 ratio of M to M+2. So the next clue here is that we have what I would consider a significant contribution of M+1 at 168 with 4.4% abundance. And so what we can infer from that is M+1 contribution is due to carbon 13, which is present in a natural abundance of 1.1%. So let's capture that significant M+1 contribution due to the 1.1% natural abundance of C13. So again, the naturally occurring isotope that's most abundant is carbon 12. So the next isotope is carbon 13, and that's present in 1.1% abundance. So what that allows us to do is determine the number of carbon in the 153 remaining from step 1. So how do we do that? Well, we can use this equation. So this is in your book. So number of carbon, we can take the following quotient. We take the percent abundance of the M+1 peak, divide that by the parent peak M, and that whole thing we then divide by 1.1, which we get from the natural abundance of the C13. So when we plug that into the numbers we have 4.4 because that's our M plus 1 was 4.4% abundance, that goes there. Then we're going to divide that by the 50, and we're going to take that whole thing and divide it by 1.1. And actually that comes out nice and even to 8. So 8 is the total number of carbon. So we can now back calculate the number atomic mass contribution of carbon to that 153. If we take 12 times 8, that gets us 96. So this is contribution of carbon to the 153. So in our next step, we can basically do the following. So 153 minus 96, that gets us 57 mass units for remaining elements. And so we know hydrogen has to be in there. But another element must be present as well for the following reason. So we've been using the alkane saturated formula. So for 8 carbons, using the CnH2n plus 2, that will give us the max number of hydrogens that can be present. So we take 8, that gets us 16, 17, 18. So that's the max number of hydrogens. But the issue is we have 57 mass units to account for. And so if we were to take 18 due to hydrogen, that gets us 39 remaining mass units. So the question then is which element? So what we're going to do is just make an assumption that it's oxygen. And the assumption is based on most organic compounds are composed of obviously carbon, hydrogen, and then nitrogen, oxygen are probably the two most prevalent next elements. And we already saw from our inference number 2 here that there's no halogens because there's the lack of the M plus 2 peak. So what we need to do is really figure out the ratio now between the hydrogens and the oxygens. So let's use the following logic to do that. So let's set up some columns. So oxygen number, so 1, and I'm going to times this by 16, that's the atomic mass. So that gets us 16. So we're dealing with, again, 39 we have to figure out. So 39 minus whatever was in the second column, that gets us plus 23. So again, since this number is positive, that means we still have mass to account for. And so it really can't be 1 oxygen. What about 2? That gets us 2 times 16 is 32. Then we're going to take 39 minus 32. That gets us plus 7. So again, the logic is that because this number is positive, then that can't be the oxygen contribution, because we have to account for that mass. So let's do the following. We're going to take 3 oxygens times 16, that's going to get us 48. And I apologize, my son is babbling in the next room. So we're going to take 39 minus 48. Now that's going to give us a negative number, -9. And so what we can basically assume now is that there's 3 oxygens. They contribute 48. So because this sign has inverted, must reduce the number of max hydrogens is a way to think about it. So again, we were dealing with 57 mass units. 18 was the maximum number of hydrogens. And so we figured out from 3 oxygens that could contribute 48. So 57 minus 57 minus 48, that's the contribution of oxygen. That gets us +9, so that has to be the contribution of hydrogen. So we would end up with a proposed molecular formula, C8H9N1O3. So this molecular formula, if we multiply by 12, we get 96, plus the 9, plus the 14, plus the 48. That gets us the 167. So based on using all of these clues and some chemical intuition, we would arrive at the answer C8H9N1O3. So overall, this has been a problem from the Wiley plus Orion, where we propose a molecular formula given some data.